Hi. So I'll just start in a few minutes. In the meantime, if you guys have any questions, feel free to ask. And this one is just mostly something from last class. So anyway, yeah, you're right. It will give you the type name of A, B, and C. That's integer, double, and float. That's correct.
Good evening, sir.
Yeah. Hi. Yes.
Sir, regarding the questions, I was not able to attend all the 12 sessions, sir. This was the last session I'm attending, sir. Because I was busy with some other work, my college work. I'm an academician, sir. So I was busy with work. So this last session I'm attending. I've got a session, final exam on 17th, 25th April, sir. 25th April afternoon session, sir.
Okay.
This regarding week 12 session, sir. This recording session is for week 12, right? Am I right?
Right. Right. Yes.
Right, sir. So we will discuss on. I've got less time on viewing through the videos, sir. So only I'm interested in
Okay.
attending these sessions, sir. This session, at least this session, I'm able to attend. Right, sir. Uh,
Okay. Okay.
Can you briefly overview the things? What will be the things? Then we'll go. We'll have a session, sir. Then you can go through the questions, and we'll be having a session, sir.
Okay. So my plan today is to cover lambda expressions and smart pointers. Something I started last class was a brief introduction to lambda expressions. Today I'll be covering the rest of them. And other than that, you can go through my whatever sessions I had last, like previous weeks. You'll get more or less the basics of this course in NPTEL. So the thing is, the full course is actually available in I think you can get in YouTube also and through the NPTEL website. These sessions are mostly just doubt clearing, but I also just give you examples as to on certain topics, not all of them, but more or less try to cover certain topics in just more detail. Yeah, this is mostly just a TA session. It's okay if you were not able to attend also. It's just mostly for doubt clearing anyway. Yeah.
Thank you, sir. Sir, can you
Yeah.
brief on templates, template class templates, user-defined templates, and I am also interested in lambda expressions and there's something like IO manip, something they're doing, sir. And mutex, and I'm also unable to solve the week 12 session assignment 3, sir. Assignment 3, programming assignment 3. It's giving wrongly. Whatever I give, it's giving wrongly. Whatever I try to do anything, lock, they give lock something, log mts dot unlock, standard mutex, SGD colon mutex something I'm giving.
Mm.
And I'm locking, unlocking, but I'm unable to solve the programming assignment of uh, assignment 12th, week 12 programming assignment 3 is there.
Okay.
So that also if you brief on mutex and sharing, that also if you brief on, it will be nice, sir. Thank you, sir.
Okay, sure. Right. Mutex is something not I don't cover normally in the TA sessions, but okay, I can maybe look at it. Now the thing is, assignments I am not. Um, I mean, it's not something I set. It's set by the other TAs. So I can't really discuss the answer, but maybe I can give you the uh, concept at least. Let me just quickly read, check something. Uh, yeah. Okay, covering something totally starting from mutex will not be possible for me because that will take require some more things. Um, well, okay, anyway.
It's
The
okay,
main
sir. You
thing,
continue the sessions. The lambda expressions. I also don't know about lambda expressions. It will be fine. You will continue the session, sir. I'm here to. I'm here to. I will be hearing to you, sir. I'm listening to
okay,
you, sir.
sure, okay. Uh, Other than that, templates, right? I can just briefly go over templates and anyway, I'll start with just lambda expression, initialize list and all that. Anyway, I'll just ignore for today. I'll just give a brief on lambda expression and continue for the class. Templates I can cover shortly. Okay, so the idea is that let's say you have a max function. It takes two inputs A and B. Let's say both are integers, right? And the output is also an integer. Okay. The body of the function looks something like this. This is a ternary operator, okay, which returns the true clause and the false clause. On the left to the ternary operator, you have something called a comparison. So you have A and B, okay. So and let's say you can compare these two numbers, which say, and this statement in particular here says if A is greater than B, so if A is greater than B, then this part becomes true, okay. And if it's true, you get A as a return, which means if A is greater than B, you return A, which should happen if you have a max function. But if A is not greater than B, so it could be equal or less, okay, then you should return B, right? Now, the thing to note, the return body is exactly the same if you have a different data type for A and B also. So even if you're returning A and B, which are of different data types, okay, and let's say they're double, the body of it does not change, right? So it just seems redundant to write the same logic and the same function many times for every data type, right? Exactly for the same thing, we have templates. Okay. So this is a macro. Let's not worry about that. So the syntax for template looks something like this. So you have a max function and you define a template with type name T. What this T is, T, you can think of T as a variable, like we define integer A, right? Like something like integer A. I'm defining the data type as T. Okay, so T itself is the name of my data type. Okay, so I have a data type T. I'm defining A as the data type T. Okay, B also here is also of the data type T. The data type that gets returned will also naturally be of T, right? And the nice thing is the body is the same, which just says that if I have integers, if I have uh, doubles, float, or any other data type, inbuilt data type, all these are inbuilt data types. Okay, they're available in the language. In any of these data types, I can do this comparison. Okay, if it's allowed, right? If it's allowed, if you can do comparison, then this body will return the max of them, of those, or any of the input numbers. So the nice thing is, because of templates, you don't need to rewrite the same thing many times. And the good thing, I will have, so, okay. And another very important thing to remember about templates is templates like here, in this case, they actually don't exist in memory. Okay. Unless you actually, you explicitly instantiate them. What does that mean? So for example, if I don't use this max function at all in my code, and the function definition like this just exists before the main function, you can think that way. This will not do anything. I mean, the compiler doesn't need to compile this because it was never used. But if you had normal functions like this, they need to be compiled, all of this. Okay. When you have templates, let's say, for example, I take main here. Ignore this line for now. Okay. Don't worry about it. I'll come to it. Just imagine that you have the include function, you have this portion of the code, and then this main function. Okay. You have integer and double. Some numbers I've defined. I'll take the max function. Okay. Next, I'll have a template uh, parameter here. So this is the syntax for using templates. You take the name of the function, you pass the template parameters and the input parameters. Okay, that's it. Very similarly, you have the max function, the input parameter for the template, and then the inputs, right? Let's say I just had the int function. I do not have this line. So let's say I just comment this. This does not exist. And all of this, let's say it does not exist, something like that. Okay. Only this line. Okay. So let's say only this line exists where it says, I want A and B, okay, as the input and integer as the template. So a specific version of this templatized function exists, which is the integer version of it. Okay. As such, template do not have they don't have any specific compiled symbol existing which exists in the compiler. Okay. If you specifically instantiate integer, uh, everywhere t is replaced with integer. Okay. And the specific version of that gets compiled. That's it. The nice thing because of this is if I don't use the double version anywhere, okay, that will not take space in my code, my binary, compiled binary. Okay. That's a very powerful thing. You can actually reduce the compiled size of your executable. Again, wherever necessary. It's not always we care about these things, but there are situations where one needs to care about such things. Okay. So simple enough. You have integers, you input two numbers, and the specific version of that max function gets compiled, and everything is all good. And that same definition of the body is used for all kinds of templates for integer, double, and so forth. Similarly, if I have double here, okay, it compiles a version of double. All right, that's how you think of using templatized functions. The other
Yes,
nice thing,
sir. Can you
yeah,
give class instead of type name? Can you give template class T also can give right, sir?
you
Template
can,
within that less than
like
greater than symbol can give class T also can give right.
you can, yeah, yes.
Mm.
Type name is just
Moreover,
another.
nowadays for int it will give it will not do the max function right, sir. That now for int it will not do the max function. For double element it will do the max function right.
No, it will
This
do for
program,
both.
this program.
This program, if I take as such, then it does for both for integer and double. It's essentially like it creates one copy for integer, another copy for double.
No, sir. The rest part template that int you have given, right?
Mhm.
That is written zero only, right? That written zero only. Doesn't do the ternary operation that a greater than b, then a, the else b. That doesn't do in the whole program. I'm saying, sir.
Oh, okay, okay, whole program. Yeah. So here, okay, yeah, this is a specific example I'm giving where I'm saying that even if integer versions of my class can exist, okay, with this definition, I have specifically instantiated my template with for the integer part, okay, by giving integers here and returning always zero. So this, yes, that you are right. This version will always return zero. That's correct. Yeah. So this is a specific instantiation. So if I call the integer version of it, because this specific version exists, okay, this version does not get compiled for integer because it's already been done. Okay. But for the rest of the cases, wherever I pass uh, some template parameter and let's say a specific instance of that function of the templatized function does not exist. Let's say for double doesn't exist. So it will compile this body with the function double. Yeah, that's correct. Yeah. Yeah. Another thing is, let's say I just pass A and B because the types here are determined by the during compilation, you are actually passing the strongly typed data type. So it knows A is integer, B is integer. So it knows that the return type will also be integer. So because it can figure out this data type T at compilation time, you can sometimes ignore the explicit uh, putting of explicit passing of the template parameter like integer and double here. So line this 17 and line 20 are exactly the same. They're equivalent. Similarly, line 18 and line 21. Yeah. And then you can also implicitly cast, say, for example, A and B are integers. So the max of them will also return integer. But I can store them in double and the vice versa. Yeah. Typecasting is something we covered before that. So specifically here, this is implicit typecasting. And yeah. That's more or less the idea about templates.
Thank you, sir. Thank you, sir. Sir,
Yeah.
regarding inheritance, sir, I have a doubt in inheritance. For
Sure.
example, if you instantiate a derived class from base class,
Mm.
for example, virtual, we use virtual functions or without using virtual functions.
Right.
I've got a doubt in that also. But you can continue these sessions. Then we can have lastly we can have a question Q&A session, no sir. That time we can discuss, no sir.
Yeah, sure. That's fine. Or you can go ahead and ask me. That's fine.
Yes, sir. Regarding inheritance, that when you are using virtual functions or
Mm.
without using virtual functions, what will be the inheritance affected? Inheritance, for example, if you get a base class, if you
Mm.
call a base class from a derived class,
Mm.
uh, sir,
Yeah, sorry.
base class from a derived class, what will be your for example, I got something. Uh, some functions are present in the base class and some functions are present in the derived class.
Right.
And we have a pointer something, or we create an instantiation of a base
Mm-hmm.
class and call the derived class. Then
Right.
we call the function of a derived class. Then
Yes.
what will be your output like that, sir?
Okay. I can just give point you towards this example. So let's say base class has these members, a private member with data 1B, public member with data 2B, and protected member with data 3B. Okay. And we make a derived class from base class with data 1D as a member for derived class. By definition, if you don't provide anything, this is also private. Okay. And let's say the public member is data 2D. Furthermore, I have a function, okay, func, which accesses data 1D, data 2D, data 3D, and all these numbers. Specifically, I use a this pointer. The only thing to remember here for the this pointer is that it refers to the derived classes object. So when I say this one data 1D, I'm referring to this guy actually, which is owned by derived. Data 2D, which is owned by derived. Data 3D, again, which is owned by derived. Okay, like that. And this is data 3D here. I can actually try accessing data 1B, data 2B, data 3B also. Reason being, whenever, so when I say B, they're actually owned by base class. Yes. But if I have a derived class, which is inherited from base class, the inheritance, the property, this is a property of inheritance. It also inherits all the member variables of your base class. Okay. Because of that, now derived class itself has a copy of data 1B, itself has a copy of 2B, itself has a copy of data 3B. All right. So that this pointer is specifically trying to refer to those members which are inherited by data derived class. Okay. This is all. That's all you have to. So, and then this example basically says how you can access something or not. Private members are only accessible by that class itself. So data 1B cannot be accessed by derived class because that is part of base class actually. So even if it inherits it, you cannot access the member. Data 2B public, so not a problem. Data 3B protected, also fine because protected members are can be derived and accessed. Okay, so this is something just remember, and any function also gets derived. So these are data members. Functions also get derived, and when you try to access them through pointers or any other thing, exact same logic applies. You can access the functions that form the derived class object, which are derived from the base class. Then you just have to make sure that function overloading, like I have an example, probably, no, not this one. Yeah, function overriding and function overloading will take place. Just you have to be careful what definition is getting called. You can have a function f and g in the base class. You can have function f, g, h, same exact functions in derived class. You can have extra functions in derived class. Now, when what happens here is name of function, type of function, and the input parameters. This whole thing specifies what your function is. So you have void f integer I, exactly the same thing, right? So the precedence is this line of definition. But if you call f from derived class, it will use this body, not this body. So this is what overriding is. But if you see G, it is void G integer I. Here it is void G, but float I. Okay. So same function name having taking two different input parameters is fine because that is function overloading. So depending on from derived class only, like all these examples, if I call G with float, it will use this body. But if I call G with integer input, it will use this body. Okay. And H also exists. So you can freely use that. Essentially, this is the idea. You have to understand about function overloading and overriding and yeah, do the solve the problem accordingly. Okay.
Right, sir. Thank you, sir. Sir, for example, if you are calling b dot f of 1, it will print only one, it will print 1, right? I colon 1, it will print. But
It will print this one. If you
no,
have it, no, if you're
no,
using
b
b
b
dot
dot f of 1,
b dot
first
perfect,
one.
yes, that's correct. Yes, b, if you're using b, then yes.
But if you do derived, it will go to base class, then it will come to derived class. It will print I colon 1, I minus 1 again, it will print 2 times.
No, it won't. So uh, there's only one f that can exist because f, if you take this uh, definition, then it is return type is a void. The name of the function is f. The input is I. Okay. Very similarly, here it is exactly the same. So both definitions cannot exist together. In this case, what happens is because base base classes function also get inherited by the derived class, and this collision is happening. So the standard says I will use the derived classes definition. That's it.
To
So
know
if you
both the
use
classes won't be, both the functions won't be printed. Only one
see,
function only will be every time. Only one function only will be considered.
yes, that's correct.
And another question, sir.
First, let me
For example, for G also
because
it's the same applies, sir.
yeah, but here it is different. That's what I'm saying. Why is that so? Like, why should one exist and not the other? Because if you take f for a function to be unique, okay, what makes f and g different? The name is different, of course. The second point is the inputs are different, may or may not be different. So if you take f and it has another definition for not just integer, for double, that's a different function. It's not the same function, even if the name is same. You can have different return types also. Okay. So void f and input parameter uniquely makes a function, which is exactly the same here. Hence, in this specific case, this is function overriding because you're using the same exact function, inheriting the same exact function from your base class. But for G, it is not the case because your input parameter is different. So both definition of G exists for derived class. So depending on which input you're giving to G, if it's a float, it'll use this definition. If it's integer, then it will use this definition. Okay.
Thank you, sir. Thank you, sir.
Yeah. Okay, I guess there should be more. Okay. Let's continue with the class. I can take questions later on. I'll give a brief overview of lambda expressions and then other auto type data types I'll just ignore for now. That should be okay for today. Yeah, the idea with lambda expression, let me go with, I'll not worry about functors and other stuff. Okay. I'll directly jump to the syntax that I started last class. Okay. So recap, lambda expressions. So the syntax looks something like this. First, you have the square bracket, which has the capture list. Okay. Then you have the parameter list with the small brackets. Okay. And the return type. And then finally, with the curly braces, the body. Simple syntax, but what does it do? So let's say I have all this empty. So the capture list, parameter list for now is empty. Just have the body. Okay. We'll make it complicated as I go. So the curly braces inside has the body of the function. So that's standard cout hello world. Fine. The return type of this, okay, will be something. I don't need to worry about it. I'm just using auto for it. Whatever it is, at compilation time, it can be known. So I'll just use auto to capture that. So essentially, this is a print function. Okay, I don't need to worry about making it a full-time function like we saw before, right? So the max function that we saw just now. So instead of making full-fledged functions, to have temporary functions, that is the lambda expression. So this is also a function which does the body, whatever the body does, which is printing this hello world. Okay, so this is the print function name. We are putting it some name. To access this multiple times, use the name and use it like a function. It does not take any input. Okay, it's empty. So you don't need to pass anything here and just use those two brackets and call it as many times. So this hello world will get printed, or this function will get called that many number of times. Okay, so this is what a lambda expression is. Furthermore, because from here to here, okay, whatever I have selected just now is my lambda expression, which then that means I can print, I can put everything here, and just if I put this extra bracket, this is a valid syntax, this whole thing. Instead of, just think of it like instead of print, I actually put the whole lambda expression. And to call this function again, I use the brackets like this. So this whole thing will print hello world too. That's it. Right? This example is mostly just to make you understand how the syntax and expressions work. Now, will you be doing this exact syntax or not? That's a different thing. Okay. More important thing is to understand the actual underlying principles. Okay. Right. So moving on, let's take more examples. So this is the syntax. On top of this, we'll build the more things. Yeah. Okay. So I stream as usual to print stuff out of the main function. Then yeah. So let's say there's a if condition, which is itself a lambda expression. So the capture list, some input. Oh, sorry. Did I mistake? No, it's fine. No. Then some body. Okay. And yeah, that's it. So this lambda expression takes two integers, integer A and integer B. Okay. Now the body part. Body is essentially returns the comparison if A is equal to B. Okay. And you have to remember to end with semicolon. Okay. And now the important part, because this whole thing is a lambda expression. Okay. I can choose to just pass parameters and use it right here. I'll pass 8, 8. So this lambda expression gets checked with this parameter 8, 8. So the input parameter here will, in this place here, it will be 8, 8, and it returns if A equals to B, which is true in this case. Okay. So you get standard cout true statement, because if it's true, if the if condition holds, then you should get true statement, right? Okay. Then else part. And if it's otherwise, then yeah, a false statement. Okay. Then yeah, stand cout. I can make yeah, the lesser of, let's say, 8,6. Okay. In the complete thing, I'll make another lambda expression. No capture list, parameters takes A and B, and the body goes like this. In here itself, I have the ternary operator, which will be, let's say, A is less than B, then it's true, you return the lesser one, first let's say A, or else B, and end of function. That's it. Finally, I'll call this lambda expression with 8,6. Okay. I'm just giving you examples where you can use lambda expressions. There is no, uh, what do you call it? Hard and fast rule that you have to put the lambda expression in some name or something and then use it. Nothing like that. I just used it inside a single line. Okay. So this whole thing is a statement with standard C out and other pieces, where the lesser of two numbers is just compared in one line. And I've just passed the number. You could get those numbers from other inputs also. Let's say not the main function, but this whole thing, let's say the whole line complete thing is called inside some other function, which takes input as a some numbers x, y. And you could pass x and y here, let's say, which are a and b for this lambda expression, something like that. Okay? You can always keep adding stuff, more and more stuff. That's what I'm saying. Another thing you can do is you can actually give a name. Yeah, nothing wrong with that. So this is just syntax. Mm, there is no. It's just a different way of doing the same thing. Is what I'm saying. So integer a, integer b, and return a as b. And yeah, because this is auto, right? You have to end this with a semicolon. Be sure to respect the syntax. Anyway, you'll get, if you make mistakes, compiler will throw an error. So there's, so you guys know why you have to end. Okay, so this is the body, so it has to have, it has to end with semicolon. Now the clause equals to, okay, this whole thing is a lambda expression, right? So you have to end that also with a semicolon. Now, if I can do this, pretty much the same thing. Uh, Clause, okay, now we use expressions. So let's say it's 9,9, which has standard CL put statement. And then again, else you can have else the first statement. If I have, let's say, the clause as 8 and 9, so the true statement holds, and then else part, first statement. Okay. Okay. Let's just run this. Later. Okay. All right. The first statement is true. 8 is indeed equal to 8. So we get the true statement. Then the lesser of 8 and 6 gets returned, which is 6. Okay. That's correct. And yeah, for 9,9, true statement should get printed, which is happening. Oh, sorry, which is happening. And for 8,9, it should return the false statement because it is not true. Okay. That's the comparison, basically. Okay. This is another way you use lambda expression, but you have to capture the, not the capture, sorry, you have to pass the parameters. The parameter list is the other part other than the body. Okay. So this is the parameters, right? Now let's um, take the other example. So I started with the remainder operation. Okay, recalling this, we have a remainder operation takes the number n, int divides it with n, another constant number. Okay, what we're saying is the small m is constant, and we are going to divide every number which is passed here represented with capital N. Okay, and the remainder is what we want to return. Okay, so in this case, the remainder, I want basically a function remainder which takes 15 or any other number and returns me always the remainder, returns me the number when it's divided by 10. Okay, now extend that with lambda expressions. I'll have include string in yeah, let's say m is 10. Okay, now I'll make auto and make the remainder function with lambda expression equals. Now I'll be using the final piece of the syntax. So we saw the body, we saw the parameter list. Now we use the capture list. I'll pass m here itself. I have some integer. So I want the integer to be n, then the body, which is return and percentage m. Okay, that's it. And this whole thing I'll end with a semicolon because that's called the remainder function. What it does is n is something. Okay, maybe I'll just write that and show you guys. Yeah, let's say let's see out. Yeah, the remainder and remainder. Same example as before, 15 and yeah, standard inline. That's it. Yeah. Now, let's say I print this. Does it give me the correct answer? Okay, 5, that's correct. Now, important thing to remember here is that why you have two different inputs, right? If I can input n and return something, I can also pass m here, right? Makes sense? I mean, if I can have n here, nothing stops me to make uh, another part here m. Forget about all this, okay? And this will absolutely work, right? You just have to pass 10 here, okay? Or m itself because you have already defined it. This is absolutely fine. You can check that. Also works, right? But then why do we go with the capture list method anyway? So the reason for that is, let's say uh, I go with this syntax. Yeah, I think this is fine. Yeah. What this means is I can use the remainder function for many things actually. So if I pass, let's say 10 here, okay, I actually don't need to worry about passing m every time. If you think about it, I just need to pass the actual parameter, which is m, which is actually varying. What I'm trying to say is this remainder function in particular has been written so that your small m, okay, becomes a divisor always. I'll repeat that. Your remainder function here just changes what number you're dividing with. Uh, you're dividing by, as in the capital N. Okay. I'm saying the dividend. Okay. So the capital N, which is in the left side of your this percentage operator, only that number changes, and you can reuse this function many times for that number particularly. Meaning this remainder function will always divide with 10 or whatever you choose m to be. Okay. For certain case like this only, you make sure that your capture list captures m. Now once you've passed m, while defining your lambda expression, this value gets fixed. You cannot change it. Okay, that is hence a constant. Okay, you cannot change that value anymore once it's captured. Okay, so let's divide 10 by 10 also and see the result. So the first one it returns 5, and for second it returns 0 because 10 is divisible by 10, so the remainder is 0. Okay, that's sort of the essential idea. What if I make, so I had integer m defined as 10, right? What if I make m equals to 5? So now my divisor will become 5, and that is something I'll be using to divide my number by. So let's say I call the same things after changing. What do you guys think will happen? So the first two then outputs are going to be this only. That is, I think, um, no doubt there. It's just that I've added these 3 lines extra. So what do you guys think will happen? All right. It's actually the same thing. You will get the same output. Okay. Again, the reason for that is you have the number 15. It has to get divided by some number m. Turns out it has already been captured. So while defining remainder um, lambda expression itself, you have ensured that your capture list, okay, captures the number m. Whatever is the state of the number, just the value 10. That's it. This cannot be changed now. Okay, right. Yeah, so this cannot be changed now. Even if you change m to be 5 and call this remainder function, okay, you will divide your inputs with the value 10. Okay, right? So hence you see the values 5 and 0. Because if m would have been changed to 5, and let's say the lambda expression captures this new value of m again, okay, so 15 divided by 5 would have been 0. You wouldn't have had 5. Okay, for 10 it makes sense. Anyway, 10 is divisible by 10, and 10 is also divisible by 5. So, right. Okay, so that is what a capture list is. The first piece of syntax, piece in the syntax of lambda expressions, where the capture list, whatever it captures is the current value, and that is permanent for the lambda expression. Okay. Another thing you can do is I'll define it this way. Pretty much the same thing. Then return uh, the complete thing, but not this actually. So I'll define and percentage and all this done. And then finally, pass with me. Oh, sorry. Okay. So I use the lambda expression. Okay. And then to call that lambda expression, I just pass the parameter and then this ended. Okay. Can anybody tell me what will be the answer for this?
It's a m is it is m is equal to 10, then m is equal to 5. It should be 0, sir.
That's correct. Yes. This is the important thing to note. Whenever the lambda expression is created, or like in this case here with some name, and here there is no, I didn't give it a name, but in either case, the lambda expression is getting created, right? The value of n is determined by the calling of the for the parameter list is always determined whenever you call the lambda expression. So here in this case, it is 15. That is fine. But for the part which is the capture list, okay, it's the value that is captured at the creation of a lambda expression, and we are passing the value m, the variable m, which has the value 5. So this lambda expression will actually capture 5 as a divisor, not 10, because 10 was captured. 10 was the value here, which is what this guy captured. But this guy will capture the value 5. Hence, I did not make it as a const int, even though m behaves like a const for the lambda expression. Okay, that's correct. So if you print it, it should print 0. Yeah, that's what we see. All right.
Sir, I've also seen passing by reference ampersand m or something, and
Yeah,
then if it pass by reference, it gives the answer correctly, yes, sir.
I'll. That's my next example. Yes. Have the integer main, then a temporary variable. Let's say it's an integer and just put it as 0. I'll make auto sum a lambda expression. Okay, capture list something and then the body which adds to 10. Then that's it. Yeah, but in the capture list, okay. So for your lambda expression to actually see certain variables, you have to either pass them by capture or the parameter list. Okay, that is sort of the idea. So here in this case, exactly, I'm using the reference. So I'm going to pass temp as a reference to the capture list of sum. Okay, that is the idea where I call sum variable. So sum, okay. And because I'm writing to temp, I'll just keep printing temp also because that is what I have access to, right? That's the only variable I have, which is in the scope of your main function for you to access. So you have this. Pretty much the same idea. So what do you guys think will be the output? So what it does
Should
is
be,
it sorry,
it should be 15, sir.
correct. So the value of temp is 0. That's what gets captured. And we're adding n to it, where n for this sum is 15. So 15 gets added to 0. So you get answer as 15. So let's run that. That's correct. So it's 15. But what if unlike the previous case, I should not be this. I have formats. Anyway, yeah. So unlike in this case, where after changing m to 5 also did not change, right? The answer did not like, in a way change. Uh, what happens if I do the same thing here? Okay. So if he's I'll just give you the answer for this. What we say is that actually changes. The reason for that is essentially the capture list part, where we pass the capture list here by value. So what it captures m is the current value of it when the lambda expression gets created. So it is 10. So because it's 10, the remainder capture list here in this line captures the value to be 10. Because the value is 5 in this expression, the lambda function captures this
Sir,
as 5.
can I put an ampersand m there and we can see the output, sir? It will be
Yeah,
changing.
yes. Yeah, you can.
Uh,
It will not actually. So
no, sir, no, sir.
because
In the first auto reminder, can you put an ampersand there?
yeah,
Then it will be uh, actually a remainder of 15 is it should be 10. It will be
right.
10, right? 10 5 will be there, 0, and lastly then it will be 0 0, 5 0 0 0 0, 5 3 0, 3 zeros. Is it right, sir?
Uh, no, because okay, oh here, right. That is correct. Yes, that's correct. Let's run that. That's correct.
Last one also is will be
Yeah,
0 only.
that's
4
zero.
zeros.
Yes.
Right.
4 zeros. Yes, because this one captures m's current value, and again, this also did actually. Yes, that's correct. First one was 5, because 10 divided 15 divided by 10, so that's 5. 10 divided by 10 again 0. 10 15 divided by now the new value 5, so 0 and others. Yes, that's correct.
Thank you, sir. Thank you, sir.
Yeah. So for now I'll just remove this. And yeah, same very actually, yeah, and that I think also covers the same idea. So 15 gets added, and because temp is actually passed as a reference, so each time it is adding to temp is the value that is this guy. This is actual variable. Because we pass it by reference, that original place gets added up. So if we run this example, we get 30. Similarly, doing it multiple times also makes the result add up. All right, that's what it is. Okay. Now, yeah, another example. Gemini, integer some value, let's say that is 0. Okay. And let's say there's a variable called ref. I think you guys can guess where I'm going with this. I'm going to use val as passing by value and ref as passing by reference. Make auto check function lambda expression again as passing by value and passing by reference. Okay. Then parameters. Parameter 1, parameter 2, also an integer. Now, and let's see out val as value and prints the ref, then prints parameter 1, as parameter 1, then prints parameter 2, and the end of them. And the whole thing happened with a simple. Now let's say I define ref as 4, call the check function with 10 and let's say 11. Then val equals to 5. So check with again 10, 11. Finally, I'll change it up again to 70 and check 1 comma 2. Yeah, try this out. What should be the outputs?
So first one reference is equal to first value is equal to 0, sir.
Hmm.
First output will be value is equal to 0.
Hmm.
val is 0, reference is equal to again 0. First one, sir. Param
Okay,
one is check. No, first one. No. Reference equal to 4. Reference is equal to 4, sir. Reference is equal to 4.
right.
Val is equal to 0. Reference is equal to 4. Param one is 10, 11.
Yeah, that's not going to change. That's correct. The only thing that I can actually change is the reference. So that's something you have to just pay attention to. Yeah, that's correct.
So again, then the second output will be check 10, 11 is value will be again it will be 4 only. Value will be again 0 only. 0.
0 only. Yes.
0. Reference will be 5. Reference
Yes.
reference is 4 only. Reference 4 only.
Because that's changed. Correct.
And 10, 11. Then
Yes.
value will be 0 only. Reference will be 17. 1 and 2.
Yeah, because val is something that got created while getting captured. So if I change val, it should not affect anything. Yeah.
It won't change. No, sir. It won't change 0. It will be every time value will be 0.
Yes. It will always be 0. Yeah. Let's
Right,
run
sir.
this. Yeah. Confirm the output, but yeah, that's correct. So val is not going to change. It's always 0. Initially, reference had nothing, but when I called it, I set it to 4. So that's what gets set. And here I did not change anything with ref. So also 4. I changed ref again. So that's what appears for the third one. Parameters, I think, are straightforward. 10, 11, 10, 11, 1, 2. I think that's fine. Okay, that's good.
Yes, sir. Thank you, sir.
Yeah. Yeah. Final one with another example. So essentially, lambda expressions make very writing the same thing very easy, like whatever we had here, right? Getting the same format done without lambda expressions in, let's say, C or C++. Okay, it's little more complicated, but let's look at the example how to do that. Basically, we're trying to emulate lambda expression without the actual construct, right? Without the actual syntax that is provided by C++. So that the code I'm going to write, it sort of works for both C and C++ because we're going to use structs. Okay, you can use classes also. It's same thing. The idea is same. So I'll define val 0, then integer ref. I'll make a struct. Says check underscore. Now this struct and there. Then yeah, in this struct I'll make integer val underscore integer reference ref underscore make a check function constructor basically integer val integer I think reference yes reference ref is what it takes as input and sets the internal variables val underscore ref as val from val and ref so ref from ref down no pointer operator. Okay, so this is the overload, not overload, it's the operator bracket I'm actually defining. So let's give it a definition. It takes integer parameter 1, integer parameter 2, then the body, which has, I just in the last one, this whole thing. Now this works because for the given struct, it has access to val because these are inter variables, right? So it has access to val, but I have to use val f here. So if that reference f here. Okay, so it has access to val f, val underscore f. So val gets printed, ref underscore f. So ref gets printed. Parameters it takes as inputs. So this also gets printed. Okay, and this is my struct. Okay, So in the inside the main function, I just defined my struct. I could have done it outside also. It's fine. For this code, it makes no difference. Okay. Now I make an auto, which is a check, which is check underscore f, the struct. Okay. Basically an instance of this object. Create a check underscore f with these values, val and ref, which are these values, val and ref. Okay. Right. Now I'll repeat that then. Exactly the same thing, but yeah, done this way. So you just see, while this syntax makes it much cleaner, okay, to do the same thing, we have to repeat all this boilerplate code. Okay. What I'm trying to say is, you can actually achieve a lambda expression, which we had here, something like this, through a struct. This, if you go to the code actually and think about it, whatever this thing does is exactly the same as whatever we defined just before. Okay. Right. Now, because of this whole jugglery, you can achieve a lambda expression as a data structure. Okay. Same idea. Exactly. Like, I would say it's not the same, it's exactly the same idea. Just so happens that we get a proper syntax to define it, and we don't need to worry about so much boilerplate code using struct and so on and so forth. Okay. Nonetheless, you can have struct behave like a lambda expression so you can actually write this whole code in C and have lambda expressions which are not available in C.
Sir, I'm sorry to interrupt you, sir. Sir, can a struct can have a function, sir? I'm
Yeah.
really I can't understand because I've been given a structure means it's a record data type and it will have a composite heterogeneous elements and something like that. Can it have a function also, sir? Class can have a function, but structs can also can have a function.
Yeah.
Okay, okay,
Yes.
sir. Thank you, sir.
Yeah. It's, as you can think struct like a very basic class without the polymorphism, inheritance, and all that. But yeah, it can. Yes. It has a constructor uh, and basic stuff. Yeah. Right. So yeah, pretty much the same thing. So uh, I'm saying is check f is the struct, and I create an object of it. And whenever I use the bracket operator, this operator definition gets called with the parameters. So I get a lambda expression like thing what I had just before. Okay, pretty much the same. Yeah, that's it. Can run this also. Why not? And check the output. Yeah, it's 0047. So exactly the same. Right. Okay. Now let's look at smart pointers. That's more or less what I wanted to cover for lambda expressions. Yeah. Yeah. I'll define something called my class, which has, let's say, public void function, name as function, and the function does nothing. Yes, it's just empty. The main function, which is, let's say, define my class, okay, my class, and the object I just passed EJ. Then I'll have, let's say, my class pointer, okay, custom pointer. Now it should be object pointer, and I'll define a new my class. So define So this my class is used as the base, okay? And the new keyword assigns some memory, returns a pointer to this class, and that is stored inside the object pointer in this variable. And the data type will naturally be my class pointer. You can use auto, but I'm going to be more specific here. Okay. And for example, and let's say you accidentally do this, uh, which is actually allowed, but let's say you do this. Okay. So done. The actually you could use null pointer here. Object vector null ptr. Yeah. Okay. So this was fine. If you just see this line, I had defined an obj of data type my class. No problem. That's all good. Fine. But this is also valid syntax, line 11, where I'm creating a my class object with a new keyword and returning the pointer to it to be stored in object pointer. Absolutely valid. But it is possible that you could reset object pointer to some null pointer or maybe to some other value. Okay. Because of this, now what happens is whatever the object was pointing, object PTR was pointing to, that is dangling. There is no ownership for it. Nobody owns it anymore. And it's just there. You cannot delete it because there's no access to that pointer address anyway. Okay. So this is actually an example of memory leak. Okay? In assignment, as an assignment operator, due to assignment operator. Oh, first, say this creates ownership. Loses ownership. Okay.
Sir, if I call a destructor there, sir, public, you can call a destructor there in my class. Will it be happening that instead of will it have the will it can't be deleted at all, sir? It will not get deleted at all.
And get you. So if you think about it, the my class object here, okay, that gets created. That is fine. So the default constructor gets called for this class. That is fine. And this object is inside the scope of these two brackets. So when your program ends, the destructor for object gets called, so that gets free. Not a problem. What about the class that got created due to my class? Right. Its pointer was assigned to object pointer, but the scope of that variable was never there at all. So even if your program actually ends, this is actually a bad code because the object that was created will never get freed. Right.
Right, sir. Right, sir. Thank you, sir. Right, sir.
Yeah. So if I just run it, it'll run, but again, I just ran a bad code. Another thing one can do is something like this. This is one example where memory leak assignment happened. Uh, I'll give an error with copy. So there was memory leak with assignment. I'll give another example of error with copy. And this actually motivates why we need smart pointers and why were they introduced in C++. So actually a lot of problems with language, like let's say people associate with languages like C and C++ is that memory management is not automatic and you have to be careful and do it. But actually, if you start using smart pointers, a lot of these problems actually go away. Okay. So we're going to motivate why, how does that work? Okay. And a lot of these things are, why are they not, they're actually automatically managed. So to motivate that, let's take these examples. So we'll have new my class. Yeah, and this again creates ownership. Object pointer here. Uh, that should be okay. Yeah, I defined it here. I erase it. Yeah. Okay. So I can set it to A actually. So I create a new my class object and sort of assign its pointer to A. So I can do this. I can store the object pointer here. Okay. So my object pointer is already leaking data. That's fine. It did something. But I'll reuse this object pointer now to store A itself. Okay. And now let's say I excuse me. I'll have my class pointer B also storing A. Let's say. And what we did is copy ownership. And let's say it was not there. And I set object pointer, whatever it was, with A. So this will also essentially be like losing ownership, even if null pointer was there. Okay? You're still losing ownership here. Not
So
particularly in
do
this.
we need to specify ampersand A or just A is enough, sir? My class star B is equal to A or ampersand A we have to give over.
No, that is fine because A is a pointer, right? And object pointer is also the same data type pointer.
Right, sir,
So
right, sir, right, sir.
yeah, A actually stores the address, which is of data type my class. Okay. And since A stores the address, object pointer also stores the address. So this is valid. Then yeah, I copy ownership. And also let's say what we do is suddenly we just say A equals to null pointer. That's bad, of course. So you first created A, stored it in object pointer, stored A and B, and let's say you just set A equals to null pointer. Of course, you are having a memory leak here. Okay, you can do that. I mean, you can have a situation like that here. Furthermore, let's say you just delete B. So now the only guy who was owning A, right? I had stored A and B, right? Now I just deleted B also. So yeah, the object that was originally assigned to A is nowhere now. Its original pointer was set to null pointer, and the copy that I already had also got deleted. Again, a problem, right? So this deletes the object pointed by B. Okay, so it removes ownership. True. And let's say you want to delete A. Yeah, that's a bad idea because it's already set to null and you're trying to do a double deletion. Okay, because actually another I'd set B to be A, right? And I deleted B. So technically speaking, if let's say this guy is not there, so if I delete B, I'm technically deleting A also, right? Because that's a copy. So if you do this, this is also a very big error. It's called double deletion. Not good. You cannot delete same object twice. Okay, right? So I'll just give a very brief plan about the solution as to how you can go about taking care of all this. Okay. Because pointers are involved, we need to have checks for it, right? That is what the solution is basically presenting. So solution, I have void function func that has, let's say, uh, okay, this will be, yeah, let's do it. My class pointer a equals to 0. My class pointer b can put, I think, null pointer also. That's should be okay. Yeah. Then you use try and capture. So you try and see if it actually throws an error or not. Is new my class. That's it. And try to access the. So remember, A has function also, right? So you can try accessing that function through A and just land it. Yeah, that's it. And this. Oh yeah. Furthermore, you can also try pretty much the same thing with B. And catch everything and delete. If not, so delete A, delete B, and throw. Yeah, then this is for the try. Try done. This is done. This is for the functions end. Yeah, that's it. Yeah, if it tries and crash the capture and delete. Yeah, that's it. So this more or less takes care of. We have to do a lot of managing to think that okay, I'll check if my functions are sorry, if my pointers are valid pointers, or do I need to delete them to check something if it's not done? Things like that, right? Gets a little cumbersome. Works, yes, but it gets a little cumbersome. So hence, there is a nicer way of trying to achieve the same thing. So this is the first method, well, which is little cumbersome. Uh, Second method, little more cleaner. So that is something we'll be using for, and also this is particular to C++. So let's look at that. We'll be using two definitions, RAII, which is resource, sorry, realization with initialization, and RRID, resource release is destruction. Okay. So using these principles, which are inbuilt to C++, we'll be creating smart pointers. Okay. Let's write a template class. So let's say class T. Class is smart pointer. We wanted to work for different templates, so Let's make the class a template. Private variable, t pointer, tptr, public uh, parts where I have the constructor, very important, needs to be there. So t pointer, that takes t ptr, which sets ptr variable using underscore ptr. And then the so this is essentially array sorry. So when resource gets uh, acquired through the constructor, that's when it gets initialized. So ptr gets initialized when resource, which is underscore ptr, gets captured. We'll see in more detail how does this work. And we have to make a destructor also. Okay, that's when what we'll do is have a body actually which deletes ptr. So this is what sorry, RRID is, which is basically resource release. Okay, so the destructor gets called of your object. That's why we're trying to release the your resource that happens during the destruction, because ptr now holds the actual pointer. So the destructor will call this part and then destroy it. So let's look at how to use this in practice. So this is smart pointer, or yeah, let's say I have the pointer, some operator, and not this actually. I want this guy to use capture this guy, which will be the const captures this also that. The input is nothing actually. Oh, no, that's yeah, it's nothing. The body, which is this one, pointer. Okay. And the upside operator, just the ampersand. Let's say this is some just extra definitions. Body and return ptr with the reference, because we want to reference that pointer. Okay. Now we have all the ingredients to use that pointer. So I can call the main function. I create a smart pointer object through the my class name and sp. So this is a smart pointer. Captures my new class. Okay. And sp. I can use function, call this, and here. That's it. I'm not going to compile this and show you this, but you can sort of see the rough idea here. The important thing here is let's start with the main function. It calls smart pointer class with templatized my class. Okay. So what I'm saying is the data type of PTR will be the my class that I defined before. Like for example here. And we are trying to solve this issue of all these memory leaks and other problems through that smart pointer. How do we do that? Because my class is my yeah, sorry, not the custom data type of object pointer and A, B, and everything. So this is the data type I've chosen for my smart pointer to wrap. Okay. So smart pointer now captures this class as the base, as a template actually, and everything will work around it. So created SP as the smart pointer. Okay. And new my class will create an object of my class and return a pointer to it. Right. So SP will now capture that. So this is when the constructor of smart pointer gets called, which captures underscore PTR, which is whatever this guy returns. Okay, so that is what underscore PTR is. And because this resource was this resource acquisition happened, okay, so we are setting PTR, which is the internal variable of this SP, right, to this guy. So resource acquisition, right, we used for initialization, right? Very similar. And we can use SP's function, like this arrow operation and all, to actually return the pointer that we own, right? So that pointer now returns t pointer. So t pointer's own function now we can access. Is so what we have actually done is whatever this pointer would have been, new class, new my class would have returned. Okay. We have made a wrapper around it with SP in a safe way, right? So using this, now my class SP object, the object of this class smart pointer SP owns this pointer through the RAI. Okay. So that is taken care of. That's point one. Second point, due to writing functions like this, I can access whatever the member functions of my class object would have been through SP itself also by writing some extra functions. Okay, so that's number two. So that's point number two taken care of. Third thing is, once this scope of SP ends from here to here, right? Now the destructor of SP, which is of class smart pointer, right? So this line will get called, which has a delete line for the pointer. So reserves, when we want to release, it is actually done through destruction of the pointer. So the new my class, okay, whatever pointer it had released is now safely deleted, and it all happens automatically. We don't need to worry about worry about explicitly deleting it or running into issues where it might get deleted double time, or any other such thing. Okay, right. This is the short of it. So what we see here is the power of smart pointers, where
Sir, can you know something about the copy considers? I know it's a parametric considers I can know, but what is a copy consider, sir? Can you give a brief intro of that now?
what
You have included a point a constructor here, and this is a parametric constructor. It's a parametric constructor, but I want to know how to use copy constructor, sir.
a copy is actually this, not using any moves. We are actually copying that whatever we are passing to copying from underscore pointer to a pointer. We don't need to worry about copy or move constructor right now. The essential idea is that we're using just copy constructor to copy the pointer actually here to a different place. Like another variable just owns that address, yeah, owns a copy of that address. So as long as you're deleting the same address, it's okay if the original variable is not present anymore. So so I should put it here. Yeah. Yeah. So specifically, okay, now there are a lot of features to smart pointers, and because there are a lot of other like what is it? Specific use cases for each of these smart pointers. Uh, C++ has uniquely defined, I mean, in the standard template library. So we are just going to see those and use them. You can actually implement your own way, but yeah, C++ provides already it in the STL library. So let's look at uh, one how to use. So I'll have struct foo, which has, let's say, this, where count foo, then the destructor, which is, let's say, standard out, and the destructor symbol. Say that the destructor actually was called what? I'll have the void bar and standard out foo bar. We're calling the bar sorry, function from foo. So foo bar and then also as out where style f with const and reference, which is sorry, this is standard inline. The main standard unique pointer. That's why I use the memory header that has unique pointer, which takes foo and makes a unique pointer out of it. So smart pointer SPTR, which is made by standard make unique underscore unique and this takes foo with the function. Like, so yeah, so this is in C++ 14 standard where SPTR owns the object of foo. It's another way, which also can be you can use the same another syntax, which is unique pointer taking foo, right, and s pointer. Everything here exactly the same, but instead of make unique, we're just passing new foo. So the raw pointer that gets the capture from foo, okay, that gets captured by s pointer in constructing the new standard unique pointer. Okay, so this is from C++ 11. Also the same thing, s pointer was the object. So this syntax was introduced in C++ 11, and from C++ 14 you can use this syntax much cleaner. So yeah. Now to check if s pointer is not empty. Okay, so Hence we do this. Then we can call as pointers bar function. Yeah, bar is function. So furthermore, what I'll do is use empty scope, okay, and make these things. So standard unique pointer. So call it QPTR and standard move. Now pointer actually gets moved. FPTR. I can try calling the bar function. Call the F function, which is this guy, right? By dereferencing the key point. Okay, all good. Then the S pointer again has use the standard move. So essentially changing ownership using standard move. So like that also. So better. Now we have C out. It says destroying because it's going out of scope, so destroying Jupyter. If you see, Jupyter only exists inside this scope. Okay, so as soon as it goes out of scope, Jupyter gets bye bye. And that's end line. If now let's choose again. If as pointer, then this. If it is not null, then it will print bar. Okay, and here finally take s pointer goes out of scope because we have reached the end of main function, right? And s pointer was defined only in this scope of main. Okay. This is yeah, that's good. So that of scope and yes, that's right. Okay. Now let's compile this. Have some issues. And yeah, my bad. So there's that. Okay. Right. Let's go through the output one by one and see how this thing will work. Yeah. So just give me a second. Let's look at the output. So first of all, using foo as a template, we create the s pointer. So basically, it's a object of it's actually a wrapper around a pointer pointing to the object of foo. Okay, and we're doing it cleanly. Okay. So the first one is s pointer. So we're printing bar. S pointer captures foo and it is not null because we just created it and it calls bar function of foo, right? For that, so now it prints foo bar. Okay. But important thing, first of all, the I mean that is bar, yes, but here there is a construction that is taking place, right? So when the constructor of foo gets called, it prints foo. That's what we see here. So first of all, foo gets printed because construction of foo happens. Object of foo is created using the make unique. You can think like new also does the same thing, so you'll get the same output. Okay. Then bar gets called, which prints foo bar. Okay, so that's what gets printed. Sorry, yeah. Okay. Now, when uh, you make use unique pointer again to make qptr, but you standard move sptr, it means that the pointer to this object is now uniquely owned by qptr. Again, I must repeat, unique pointer makes sure that there's only one instance of your pointer, whatever object of pointer it is wrapping around, let's say s pointer. Only one instance of it exists. Okay. You cannot have multiple copies of it, of different pointers owning the same object. That's essentially the idea. So unique pointer always make sure that only
Sir,
one.
why can't we use const, sir? Const use panna, we can use const,
Well,
const star something like that they use, no sir, for unique point, for not changing the pointers. Const star
you can, you can, yeah, you can, but there's no difference here currently because I know my pointer is going to be unique anyway. You can use it. I'm not saying denying it, but yeah, without it also, it's not like there's incorrect syntax. Yeah. So currently, so if you see here, so standard move makes sure that it takes S pointer and moves it to Q pointer. You have to use standard moves here because at a given time only S pointer is owning that object. Now we're saying that not S pointer anymore, but a Q pointer is owning this object. Okay. Now if you call bar, you can call this function now. So foo bar gets printed again. Okay. Now F with dereference of Qpedia. So foo reference gets passed. So F cons this and all that gets printed. So again, done. Finally, we move Qpedia back because if Q pointer goes out of scope, right, it destroys F, the ownership of S pointer, that same object also, because Q pointer now owns that object. If QPTR goes out of scope, that object gets destroyed. Okay. So before it gets destroyed, we moved the ownership of QPTR to SPTR. Again, even if you make mistakes here, as in do not move it back and it gets destroyed, nothing, it will work as intended and there will be no memory leak anyway. That is the beauty of doing all this. So Q pointer is not going to worry about um, bits get destroyed and it automatically, because it owns that object, the object also gets destroyed. You can try calling different functions, but they won't work here because if the actual object is already destroyed, S pointer no longer owns it. So the if condition here, the check that if it's empty, then only not empty, then only work, it will not work. It will not print bar as in foo bar, but it does because we moved it back to SPTR and then destroyed QPTR. That's what we see here. Move, and because S pointer is not empty anymore, it prints foo bar. Okay. Finally, S pointer owns the object, right? So its destructor gets called also. So underscore foo is what gets printed. Okay. Next, yeah. So other than unique pointer, there is another very important pointer. So let's learn about that. So this is shared pointer. The main difference between these unique pointer and state pointer is that, again, unique pointer just ensures that at a given time, only one pointer is pointing to the object. Shared pointers, you can have as many, like you can have multiple pointers pointing to the same object. That's the only difference. So we'll make integer p, sorry, as standard, make shared, okay, and integer with this. Now pointer p equals to 3. Now let's see out. First of all, 1 p is, so I'll have the actual value. So dereference the guy. What I did here is I created the pointer p as shared pointer and assigned the value 3 to it by dereferencing it. Okay. Then dereference it to read the value, that is the first line. The second line is 1 dot. It prints the reference count of it. Okay. So that's essentially means how many pointers are pointing to the same object. Okay. It keeps a count of it. Okay. So shared pointer have inbuilt functions for this. So you use count function to access and basically say how many pointers are pointing to the same resource we have. I can make another standard sorry, also data type. So standard shared pointer, then call it, let's say q, which takes p as the object. Okay. Now it takes p standard pointer and makes another standard pointer. So I'm saying it takes p, which is a shared pointer, and creates another shared pointer q. Now let's print this. Here's the value of q. Just dereference that now. Out. Q. Now we can print its reference count. We don't use count. And then use reference count. You dot use count. And then now another useful function, we dot reset. Okay. What does that mean? So let's look at the output for that and see the definition also. So this is the third part, is reference count. We dot use count. And line. Furthermore, let's print dot qrc. Two dot use count. And line. Now d dot. Okay, before that, let's take this example and let's the common is 1. Yeah, let's look at the output. It's part of the stop. Okay, so let's look at the output one by one. For the first one, it prints the value of p. So that is straightforward. That is 3. We made the unique, shared pointer p and set its value to be 3 by dereferencing it. So that sets the value as 3. Straightforward. The next one is printing the reference count. So that's I'm calling as RC. You can use the function useCount. It keeps a count of the number of pointers pointing to this shared pointer. So currently p useCount is 1 because only p is pointing to that object, right? The second case, what we do is we make second case, we make q out of p. Okay, and now there are 2 pointers, q and p, both pointing to the same object, right? So first of all, if you try to dereference q, it also prints 3 because the actual underlying object has the value 3, right? It's just that the 2 pointers are pointing to it. So if you dereference p, you should get that value, which is 3. If you dereference q also, you should get that same value, which is 3. Next one, uh, printing the reference count of p gives you 2. Also for q also, it also shows 2 because 2 pointers are again pointing to the same object. And both the pointers get updated value as to both pointers get updated value as to which is the reference count running for this shared object. Okay, both of them are 2. Now let's uncomment this time and see the output. Okay. So that is 0. What it means to say is because I have 2 shared pointers, okay, both referring to the same or pointing to the same object, I can actually use one of them to be reset for some other case maybe.
So
So
what
when
will
I
be the value of p, sir? P will be always be 3 only. P dot reset you are giving. So p's value will be 0. Will be
maybe it
0 or
is
p.
you can try dereferencing it and see, let's see the answer. Ideally it will be some uh that I mean it's hard to say. So again depends on the standard, but yeah, we can just see. Yeah, guess like what. Uh the reason for that is we actually did not set any value to it. Right.
P is
So
deleted. It's been deleted. P dot reset means deletes
yeah,
pointer.
yes, that's correct. So now what's happened with sorry, I should repeat this. Sorry about that. So yeah, now what happens with the number 0.3 is you have a reference count of p as set to be 0, right? So yeah, that's actually a good example. There is nothing pointing to nothing which is p is pointing to. So setting values or dereferencing it is actually exactly it's rightly giving seg fault because there is no memory it's actually pointing to. But if you take q, now it is set to 1 because still there is an original object which is owned by, maybe it was not owned by p anymore, but it's still owned by q. So there is still one pointer which is owning that q object. Again, the ownership getting destroyed is taken care of by the scope, so that is fine. But
So, sir, can you print the value of q and see whether it will have some values?
yeah, sure. Uh, we expect it to still have, sorry, we expect it to still have the original value. That's correct. So let's do that. Because if you see here, P is referring the reference count 0. It is not pointing to anything, but Q is actually pointing to something. So it will definitely give you some value, and we expect it to be the same value as what we originally saw. Okay, it prints 3, right? Okay. Now I can make another example. So sorry, not new, reset using new. I'll use integer 11, um, like as a value 11, and pass that pointer to the reset. So now P is different. Particularly, let's look at the output.
Sir, once P has been reset, right, it will be deleted now, sir. If we now give reset
Hmm.
new int of 11, will it be
Yeah.
reset? It will be again, it will be
Yes.
deleted. If we delete.
After deleted, we are allocating new memory for it to use. So P is still in the scope, so I can reuse that declaration. It just so happens that it's a capture for some underlying object, right? So the underlying object was deleted by the reset, but since I'm passing a new pointer, that new pointer gets captured. Okay. Now C out with 4 is essentially printing P, dereferencing P. Now this won't throw set fault because we have allocated new memory and new value to this new P, and we expect again. So yeah, 4. The reference count of P goes from 0 to 1 because we have allocated another object to this pointer P. So with this whole exercise, initially P was pointing to some object with a value 3. Now we create another object Q which is pointing to the same object. Now we reset P. Okay. So the original object is now owned only by Q and P is not owning anything. That's what we see here. With the new keyword, we have assigned P another underlying object. So now P and Q are currently pointing to completely different objects. And yeah, one has the value 3, another has the value 11. Okay. The reference count also also ensures what value each of these pointers are pointing to. How many numbers for the same object. So P is pointing to one object, Q is pointing to one object. And we don't have other pointers which are pointing to the same objects, right? Just one each. So the reference count stays 1 for Q1, P also 1. And furthermore, if we have, if we print the value of P, because we created a integer object pointer with the value 11, it prints 11. So,
Q will remain unsame, sir. It will be remaining same 3. It will be remaining as same as 3, right?
yes, we have not touched that value yet. So that is still 3. Yes. Yeah. Okay. Next. So P I'll set as external pointers. Okay. Now see out 5 is reference count. We don't use count. then standard and line. Okay. And yeah, can we, okay, let's see this. So again, it's set to 0. So when you assign null pointer to it, it automatically uh, deletes the underlying object. Okay. And resets its reference count to 0, which means no underlying object is actually being pointed to by P. Okay. No resource has been allocated to it anymore. Okay. And if we try to print the actual value of P, can you expect what should happen?
Segmentation fault, sir. It will be a segmentation fault only. It won't print.
Correct. Right. It's correct. It might not show up. Okay, it showed up good. So yeah, that's more or less it. All the things I want to cover for shed pointer also. I hope the idea is clear. So shed pointer P is made and we assign the value 3 to it. And then using uh, the reference counts, you can keep track of how many pointers are pointing to the current object, to any given object actually. So dereferencing the value, we are able to print the value, and using the reference count, we are able to keep track. So essentially, we create another object queue also to point to the same thing, but we removed the ownership of the same object from P so as to assign a new object to it. And again, we use null pointer to just delete that. Okay. Yeah, so that's it. And that covers the lambda expressions and smart pointers, both the topics also. And yeah, so this is the last session for this uh, run of this programming in modern C++ course. So yeah, as usual, please go through the assignments, lectures, practice more, understand the concepts, and the more you practice, the better you understand. It's something I always say. And yeah, that's more or less it. And best wishes to
Thank you, sir. Sir, one
yeah.
more thing, sir. One more thing, sir.
Yeah.
Deckel type, DECL type. That
Mm.
you can explain a little bit more, sir. If you complete with that, I will be fine, sir.
Okay. Sure. Decal type is essentially the exact type. So let's say I have integer a and pointer p. So decal type of a is integer. Okay. Decal type exactly takes the complete data type, even with the qualifier pointer. So decal type of p here will be integer pointer. So you can use decal type of a as a replacement for whatever type it has to declare another variable, for example. So B will be of data type integer. Sorry, will be of data type integer because decal type of A is integer. Similarly, decal type of P is actually integer pointer. So Q is of data type. And if we take this example, so yeah, I had given example of integer A as 10, integer reference B as let's say A. Okay, so A is integer, B is integer reference. In this case, constant, C is constant. In this case, D is constant integer reference. If you declare auto underscore a variable as auto, okay, and use a as in the right hand side, so it reduces the type of auto underscore a from type A. Okay, and the base data type in all these cases is integer. So auto only captures that. Auto captures integer for this, integer for this, integer for this, integer for this. So in all these cases, auto underscore a, b, c, d are all integers. Okay, but very similarly, if you used decal type, okay, so a is integer, so that's fine, but b is integer reference. So decal type of b returns integer reference and makes decal be as also the integer. That's the main difference. Auto only captures the base data type, but decal type captures the complete thing, including pointers, reference, constness, non-constness, everything. Okay,
Yes, sir. Okay, sir. Thank you, sir. Right, sir.
sure. Awesome. Yeah. All right. It
So
was
where it is been applied, sir? Any applications where deckel type is applied? How can it be used?
a simple example would be here. So let's say I had a data type of A and I want to exactly declare the data type of A as some other variable. More or less, that's it. It's
Oh,
like you want to not worry about the data type you already are running and just take it whatever
any
it
headers,
is.
pre-processing headers required, sir? Deckel type requires any
I
pre-processing
don't
headers?
think so. No, it's probably included in the standard header files that are included with the compiler. So right now, no. I just need an IO stream only for the standard CORs, but not for decal type. Yeah,
Thank you, sir. Thank you, sir. Sir,
sure.
and what sort of questions? The questions will be purely on multiple choice questions, multiple select questions, or will
Yeah.
there be any programming
So thing
questions?
is, yeah. So thing is, I'm not involved in question making at all, even assignments. So if you have particular questions about assignments or even like exam type pattern and all, you can ask in the forum.
Okay, sir. Thank you very much, sir. Thank you, sir. Thank you, sir.
Sure.
Shall I leave the things there? Thank you, sir.
Sure. Yeah, sure. Thank you. Yeah, so like final note, it was really enjoyable to teach you guys. So yeah, thank you everyone and happy coding.
Thank you, sir. It's a nice session, sir. Thank you, sir.